Today, I'm going to cover two topics that I wanted to explore ever since Copernicus was announced last summer: Cellular Automata and OpenCL. CAs because, well, they are a classic Entagma topic, and now we actually have a way in Houdini to build and display them directly without the use of 2D volumes or points. We can directly work with pixels here. And OpenCL because it's by far the fastest code for processing pixels that we can write in Houdini. And it's also the backbone for pretty much all of Copernicus. Now, the cellular automaton that we're going to build today is not something that I came up with myself. I first stumbled upon this on this tutorial right here by Pat Vira, and this is based on this paper by Alistair Turner, a simple model of the Belousov-Zhabotinsky reaction from first principles. And what you're seeing right here in the background is actually the pattern that the cellular automaton is going to create for us today. And you actually also might know this pattern from the NileRed logo and also this video from him. But now let's quickly talk about what this cellular automaton does and how it creates those patterns. So what we're going to do here is something that's pretty similar to pretty much one of the most famous cellular automata there is out there, the reaction diffusion cellular automaton. Again, we're going to have a diffusion step and we're going to have a reaction step, just a bit different today. Now, what's the diffusion step? The diffusion step is just there to simulate, in this case, 3 separate chemicals spreading out, moving from areas with a high concentration to areas with a low concentration. And let's call those chemicals A, B, and C for now. And then after the diffusion step, we have the reaction step. And in this case, this is a bit different compared to reaction diffusion. In here, we have 3 separate reactions for 3 separate chemicals. And if we take a look at chemical A is really good at taking chemical B and creating more chemical A. Chemical B is really good at taking some chemical C and creating more chemical B. And finally, chemical C is really good at taking some of chemical A and creating more chemical C. So in the end, we have a sort of rock, paper, scissors situation going on here. And this, in the end, is what drives all those waves and spirals that we're after here. This is the basic principle. How does that look in code? Well, it looks something like this, a bit more complicated, but we're going to work through this. First of all what we're seeing here is something that we're going to do on a per pixel basis. So first of all, again, our diffusion step. For each pixel that we're currently processing, let's say this is this pixel right here, and let's say this has an index of 0, 0. We want to get the average of a 3 by 3 pixel square around this central pixel. And this average will be the new value for this pixel. So looking at the indices, let's say this is index -1, -1, and this is index +1, +1. So in the end, for the average, we can do something like this. We can take all the values from an index of -1 to an index of +1, +1. So this entire square right here, add all those values together and divide it by 9, the total number of pixels in here, and then we get the average. And we're going to do that for all of our 3 chemicals in the end. And then in our second step, our reaction step, this tries to emulate the combination of those chemicals. This is all done by this formula. So we're going to take a blurred chemical A value and run this through this formula right here. So A is equal to A plus A times B minus C. And we're also going to clamp it between 0 and 1. And we're going to do this again for chemical A, chemical B, and chemical C. So in the end, we're going to have 3 distributions for 3 different chemicals, each with areas with a high concentration and each with areas with a low concentration. And in the end, if we say color chemical B and C both white and chemical A orange, we're going to get the same result, the same look as with the NileRed reaction to replicate here. So this is the reaction diffusion part done. This is the cellular automaton part done. Now let's quickly talk about why we want to write this in OpenCL. And in most cases, this is, I think, a pretty simple decision. This mostly boils down to 3 questions that we have to ask ourselves. So since OpenCL runs on our GPU, it's really good at processing masses of single elements in parallel. So the first question is, are we dealing with tons of points or pixels or voxels? And yes, we're definitely dealing with a lot of pixels here. Then, since OpenCL has quite a limited set of functions compared to something like Vex, we should take a look at the algorithm and it should ask us, do we have any high-level functions in here? Something like a nearpoint function in Vex, which does quite a lot of very complicated steps in the background. And again, taking a look at the algorithm, I think the most important or the most complicated function that we have in here is the class lamp function. So I think we're good here as well. And then finally, of course, OpenCL is different than Vex, and also it likes to complain a bit more than Vex. So in the end, the thing that we have to ask ourselves as well is the pain of waiting for our algorithm to finish in Vex bigger than the pain of writing the algorithm in OpenCL? And I think in this case, it's really fun to have a really fast algorithm, and it's not that much OpenCL code. So I think we're good here as well. So now with this done, let's jump into Houdini and get going. So inside an empty scene, I want to drop down a GeoNode, dive inside, and in here, drop down a COP network. And in this case, it does not really matter if you create a COP net here, or if you jump into, say, the image context inside of Houdini. This does not matter, I'm just using the OBJ context here because mainly I'm just used to it. And now let's jump inside of a COPNet and let's build a cellular automaton here. Now, first of all, before I jump into OpenCL, I want to generate some starting values for this automaton. We're dealing with 3 chemicals here. So I want to have some random starting value. And for this, I think the best idea is to use just a fractal noise. Take just some random smooth values like this. And again, since we're dealing with 3 chemicals here and we're inside the Copernicus workflow, which is set up to work with a good idea, a really efficient idea, to just think of those 3 chemicals as the red, green and blue channel of an image. So to do this, I'm going to set the signature here to RGB, and now I have 3 separate distributions for my 3 separate chemicals, my 3 color channels. This is all I want to do in here. The next thing that I want to do is I want to add a size reference to that fractal noise. Right now, our resolution for our entire canvas is 1024 by 1024. However, I want to do the cellular automata simulation on a smaller resolution. Not because it runs too slowly. Writing this in OpenCL, this is really, really fast regardless of the resolution that we're choosing up here. However, what this will do in the end is control the scale of those patterns that are going to form. So to quickly generate a size reference, I want to drop down a layer node. And the only thing on this layer node that I want to change for now is the resolution. And let's choose 256 by 256. And let's write this into the size reference. And if I now middle click on my fractal noise, I have the same size in here. And now with this done, we can drop down our OpenCL node and we can finally take a look at this. Now on this OpenCL node, the first thing that we're going to see are those 5 tabs up here. And let's quickly go through those. We have the kernel tab, and the kernel tab is just where we're going to write our OpenCL code. Then we have the options tab, and this is other additional options for how we want to run this code that we're going to write in here. And then we have the signature, the bindings, and the generated code tab. And the output or the inputs or the parameters that we find on those 3 tabs all depend on what code we're going to write in here. So actually what we're going to do to just get a feeling for this node is we're going to get rid of all the kernel code in here and also go to the signature tab and clear both the inputs and the outputs. So we have an empty OpenCL node with no inputs, no outputs, and also no image to be displayed in here. And now let's go through the kernel, through our code, and let's see also how these 3 tabs here change as well. Now, I want to create some inputs and some outputs on this node. And for this, I want to write first of all a couple of lines of code in here. That will then change some options in the signature. To add 1 layer as an input, I'm going to start with a hash symbol and bind. This is the standard way of telling OpenCL that we want to generate either a parameter or we want to load some data in, let's say through a layer in here. Then we have to tell OpenCL what data we want to bring in. In our case, this will be a layer. And then we have to give this layer a name. And for now, I'm going to call this first layer source. And later I'm going to create a second layer called destination. Now on the source layer, in front of this name, I can add some modifiers to add some additional information. In this case, what I want to add to my source layer is an ampersand, because this in the end will tell OpenCL that a layer should be both readable and writable. So we can also modify the data on this layer. Then we have to tell it what data type we want this layer to be. In our case, this will be a float 3 for our RG and B values and our 3 chemicals. And then we can also define a default value if we don't connect anything. And let's in this case write val and an equal sign and then curly brackets, and let's just initialize it to 0, 0 and 0 like this. Let's also create our second layer. This will be our output layer. So again, hashtag bind, again layer, let's call it DST, and I want to add some modifiers to this. This will be an ampersand to make also this layer right here writable. And then I also want to add a question mark at the front. And this is basically there to make this an optional input. So I don't have to connect a noodle in here to the socket to make a code run. And this is something we actually need for our destination. Then let's also make it a float 3. And again, let's set a default value, set it to 0, 0, 0, like this. And now once we have that, we can add this little, or we can click this little button right here. Now we have those inputs and outputs on our OpenCL node, and also in the signature tab, we have all the right options in here checked as well. Now, I know that all of this looks really foreign and really strange. And yes, this is absolutely true. However, there's one really great documentation article from side effects, from transitioning from Vex to OpenCL, where this is also all explained in a bit more detail. And I'm going to link this in the description as well. But for now, let's keep going with our OpenCL code in here. So let's connect up our source. And right now, OpenCL node is complaining, and it is complaining because it does not have any code to execute. So let's write this next. Now, for the code that we're going to execute, we have to define a kernel. And we do this by writing @kernel. Kernel sounds pretty scary, however in this case this just means, hey, run over every pixel in our image. This is all that this does. And then after a kernel we can again add curly brackets, and then in between those curly brackets we can actually write the code that we want to write in the end. Let's write some very simple code to just see if this all works. And for now I'm just happy to take all the right pixel values from our source image and write it to a destination image. So to do this, what I need to do is I first need to write at the DST to grab my destination. This has a function called set, where I can set those pixel values. And then in brackets, I want to grab my @source like this. And now once we have that, we can see the exact same image appearing on our OpenCL node and both on our source in here as on our destination like this. Now, since we're going to build a cellular automaton here, we want this to be able to run over and over again. So what we want to do is after we're done with our code in here, once we set our destination here, we want those values from our destination to travel all the way back to our source and be the base for our next iteration of our solve in here. And we can do this with another kernel, another special kernel called a writeback kernel. For this, I'm going to add writeback like this. And again, curly brackets. And all we want to do in here is grab this line up here and simply reverse our layers. So we want to take our source and set all those values equal to our destination. And what will now happen is our code will run through the entire code inside the kernel, save the output image somewhere in RAM, and then use the writeback kernel to write the values from our destination back to our input source like this. This is something that we also have to enable in our options. So in here we have to check use writeback kernel as well, like this. And now we're finally at the point where I can actually start writing our cellular automata code in here. So the first step that we need to do in here, and I think at that point it's also a good idea to enlarge this a bit, give us a bit more room to write a code, something like this. And the first thing that we want to do is we want to write some code that does the diffusion step of our cellular automaton. This will be just the average of a 3x3 square around a current pixel that we're currently processing. So for this, first of all, I want to create a variable called diffusion, or a diff, that is just there to store a blurred image. So for this, I'm going to create a variable. This will be a float 3. Let's call it diff. And this will be equal a default value of 0, 0, 0. However, if we apply this right now, OpenCL will complain. And the reason OpenCL is complaining is that OpenCL really wants us to specify the data type. So what we need to do is in front of a 0, 0, 0, we also have to write in parentheses float 3 like this. And now our code should be happy. Yeah, this is the first variable that I want to create. The second variable is a variable that should store the current index of the current pixel that we're processing in here. So this will be an integer 2 because we're dealing with two values, an x and a y coordinate, and also an index value. So again, integers, not floats. And let's call it p-index. And again, we have to specify our data type first, so int2. And to grab the current index of a current pixel, there are two add variables that we can use by default in OpenCL. And this will be add ix and add iy, like this. And now, once we have our current pixel, we now have to run over a 3 grid around this pixel. So for this, we're going to use some for loops. For, let's create an iterator variable. Let's call it int dy for delta on the y-axis. And this should start on -1 and it should end at +1, so smaller equals 1. And then we want to increment it. And of course, OpenCL needs to be a bit special here. It's not dy plus plus, it's plus plus dy in that case. So this is our first loops iteration. Let's create a second iteration. Let's copy this one more time. Let's indent it and let's also create the curly brackets like this. And then here we want to call it dx. And dx should start at -1, go up to 1, and also increments. And now we're running over a 3x3 grid. Now for this 3x3 grid, we want to create a new index, the index of the pixel that we're currently processing inside that 3x3 grid and inside our for loops. So again, int2, our new index, let's call it an index for neighbor index. And this should be equal to our p index plus our dx and dy. Again, we need to be very explicit with a format in here, with our data types. So again, int2, and then dx and dy like this. And then once we have our index, we want to grab the current value of our chemicals, add that pixel value, and simply add it to a whole diffusion value. So diff plus equals our add source. And to grab a pixel value from a source, we can use the buffer index function. And in here, put in our an index like this. And then once we're done here and we grabbed our pixel value, this is all just added together. Now we have to divide it by a value of 9, by our 9 pixels to get the average. So diff will be divided equal by, and in vex, I could just write 9.0. However, this is OpenCL. We have to really specify our data types. So in this case, this will be again a float 3 of 9, 9, and 9, like this. And then we can test if this part is working by setting our destination not to our add source, but instead to our diffusion. And now we should expect our image to blur somewhat. So let's hit apply here. Let's see, we have some error in here. Let's see where this went wrong. And it's p index, not p index. So let's fix this. And now this seems to work. Now, we don't see a lot of change in here, but this is simply due to this being at an iteration of 1. And if we start increasing this iteration, now we can see our image slowly blurring. And to actually make this animated, what I want to do is I want to simply add $F in here. And if I now advance my timeline, now this gets blurred more and more and more. Now, the computer science guy in me is a bit annoyed that this is the way that we're actually doing our generations of our cellular automaton in the end. Because what this basically means is that we don't use any form of caching. If we are, say, at frame 211 and we jump to frame 212, our OpenCL node will completely ignore the entire calculation of frame 211 and instead it will take the output of this node right here and run its code in here for this frame a total of 212 times to get an output picture. In theory, this is a really stupid and inefficient way to run this code. However, since this is OpenCL and OpenCL is blazing fast, this is actually a lot faster than doing something with a SOP solver and actually using a cache in Houdini. So I'm going to stick with this method in here, even if I find it a bit stupid. But for now, our diffusion is working. So now we have to worry about our reaction. We have to implement our reaction in here. So let's bring up our code window again. We talked about the reaction part earlier, and let's just implement the formula in here. Like with our diffusion up here, I want to create a variable to store my values in. A float, let's call it react for reaction. And this is equal to a float 3 that we're going to initialize with 0, 0, 0, like this. And then, first of all, we want to work on the first chemical A on this part. And we can grab this by saying react.x, as we grab the first component. And this should be equal, well, the value in a formula. So our diffusion.x plus our diffusion.x times, and in parentheses, our diffusion.y minus our diffusion.z, like this. And let's end with a semicolon. Now this is our reaction for x. Let's also create a reaction for y and z. So reaction y will be our diffusion y plus our diffusion y times our diffusion z minus our diffusion x. And our diffusion z will be equal to our diffusion z plus our diffusion z times our diffusion x minus our diffusion y, like this. And we also have to clamp those values to a 0 to 1 range, and we could do this on every line in here, or we can do this all at once. So to do this all at once, I'm going to write react is equal to clamp, and OpenCL actually has a clamp function, is equal to the clamped value of, again, our react, and you want to clamp it between a float of 3 or 0, 0, 0 and a float of 1, 1, 1, like this. And this now should be our entire code done. So let's keep our fingers crossed. Let's hit apply, no errors. And I have a feeling that this pattern in RGB values will be fairly annoying to look at, if not even dangerous for someone who is photosensitive. So what I'm going to do to make this a bit more bearable is, before I try this, I'm going to drop down RGB to mono node. And on this node, I want to grab just the red channel, just a chemical A, and then I want to use a mono to RGB node to get a color ramp. And on this color ramp, I'm going to recreate the sort of NileRedish or the reactions color scheme in the end. Let's make an orangish color here at the lower end, and let's also add some value in the middle. Make this maybe a lighter orange. And then we're going to end with white. And now let's keep our fingers crossed. Let's toggle the real time toggle in our timeline and let's hit play. And we do see nothing. Why are we seeing nothing? I have a hunch. Let's go back to our OpenCL node. And yes, like I suspected in here, I'm doing all this work to my React variable in here, and then I completely ignore it and write back my diffuse variable. Let's quickly add diffuse in here, write this to our output, and now let's see where this is getting us. And yes, this is now actually giving us the reaction. So finally, the last thing that we have to do in here is to simply enlarge this to our original resolution. For this, we're going to use a resample node, wire this in here, and let's enlarge this, let's say to 248 by 248, like this. And this is actually the slowest node in our entire setup. So again, this OpenCL in here runs really fast. And after that, we can either simply use a rub image output node to write those files to disk. Just drag the resample node in here and then set your file settings here. Or we can drop down a preview material node to quickly preview this all on some object. Let's maybe use a torus. This should wrap around this torus very nicely because this is also actually a tileable texture since we built this directly in Corps. And I think this is a quite nice looking result in the end. So this is it for today. You hopefully have some ideas on how to build your own algorithms, your own cellular automata in OpenCL, and to make them really fast. And until next time, it's cheers and goodbye. And if you like us and want to support us, or just want to learn more about Houdini in in-depth courses, consider becoming a patron of ours. And to everyone already supporting us, thanks so much guys. Without you, Entagma in this form would not be possible. Thank you.